August 2025, a 70-meter radar dish in the California desert swings toward one exact point in the sky. Goldstone Observatory, target asteroid, Nikon's 98 SA2, cruising past Earth at a safe distance, right on schedule. Astronomers had tracked this rock for 27 years. They knew precisely where it would be, down to the second. They pointed the dish, and there was nothing there. Not a glitch. Not a calibration error. The most reliable radar system on the planet, aimed at a target with 27 years of orbital data behind it, scanned empty space where a 300-meter asteroid was supposed to be sitting. For a moment, nobody knew what they were looking at. Was the dish misaligned? Was the object destroyed? Or was something else going on, something the models never accounted for? Radar tracking like this isn't guesswork. Engineers spend weeks preparing a single observation window, calculating the exact second a target should cross the beam. It's precise enough to map a rock the size of a building from tens of millions of kilometers away, which is why an empty scan felt less like a glitch and more like a warning. Here's what makes this so unsettling. Asteroids don't just wander off. Their paths are pure physics. Gravity from the sun, gravity from the planets, nothing else. Plug in the numbers and you know where the rock will be centuries from now. That's the entire foundation of tracking near-Earth objects. Predictability is the safety net that lets space agencies say, with confidence, nothing catalogued is going to hit us. 1998 SH2 just tore a hole straight through that net. When astronomers finally recovered the object using ground-based optical telescopes, they ran the numbers on how far off it truly was. 19 standard deviations. Let that sink in for a second. In statistics, 5 deviations is already enough to call something a confirmed discovery, enough to publish, enough to celebrate. 19 isn't an error bar. It's not noise, and it's not a rounding mistake. It's proof, hard mathematical proof, that something was physically pushing this object off its predicted path, and gravity alone could not explain it. So, what happened between 1998 and 2025? The trail led back to a gap. Astronomers had solid continuous data on this object from 1998 to 2016. Then, almost nothing. 9 years with barely any eyes on it at all. 9 years is more than enough time for a small, invisible force to nudge an orbit just far enough that the old math quietly stops working. And nobody would notice. There'd be no alarm, no warning sign. Just a slow drift, accumulating in silence, until the day the object simply wasn't where it should have been. That's when the real question started forming. If it isn't gravity steering this rock, what is? The team, led by navigation engineer David Farnokia at NASA's Center for Near-Earth Object Studies, went back through every image, every archived observation, every scrap of positional data ever recorded on 1998 SH2, decades of numbers nobody had reason to question until now. And buried in that data, they found a signature, a tiny, persistent thrust, the kind of push you get from gas escaping a surface unevenly, acting like a miniature, lopsided rocket engine. That's not what an asteroid does. That's what a comet does. And here's why that distinction is so much harder to prove than it sounds. Orbital simulations handle gravity beautifully. Planets, moons, even the faint push of sunlight on a rock's surface can all be modeled with near-perfect accuracy. Outgassing's different. It's chaotic. It depends on what's buried under the surface, how the object spins, which patches of ice happen to catch sunlight at which angle. You can't simulate what you can't see inside. So instead of predicting it, the team had to prove it happened after the fact by matching nearly 3 decades of position data against a version of the rock's path that finally included that hidden thrust. But here's the part that broke the textbook definition wide open. Comets are supposed to announce themselves. A glowing coma. A long bright tail streaming behind them as buried ice turns to gas in the sunlight. The classic postcard image everyone grew up with. 1998. SH2 had none of that. No tail, no coma, nothing visible in any image ever taken at any point in 27 years. And yet the thrust was there, undeniable, written directly into the object's own trajectory like a signature nobody could erase. Astronomers have a name for objects like this now. A dark comet. Something that behaves like a comet, accelerating, drifting, defying every gravity-only prediction thrown at it, while looking, in every single photograph, like a dead, silent, ordinary rock. This isn't the first one ever found. Since the category was first proposed a few years ago, researchers have identified over a dozen other dark comets hiding in plain sight across the solar system. Some are large, drifting through the outer edges of our solar system. Others are small, tucked closer to the inner planets. Each one was flagged the same way, not by seeing anything unusual, but by noticing an orbit that simply refused to match the math. But 1998 SH2 stands apart from all of them. Published in Nature Astronomy, confirmed by JPL, this case is one of the cleanest and most direct ever recorded. Not a guess, not a probability. A measured, repeated, undeniable thrust from an object carrying a spotless 27-year paper trail as nothing more than an ordinary near-Earth asteroid. Sit with that for a second. This thing hid in plain sight under a fully funded, professionally staffed tracking program for nearly 3 decades. Now here's why this isn't just a curious footnote for astronomy nerds to argue about online. NASA's Planetary Defense System, the entire network built to calculate whether something out there might one day hit Earth, runs on gravity-only models, feed in an object's current position, feed in the gravitational pull of the sun and every major planet, and the model spits out a predicted future path, decades or even centuries ahead. That's the calculation we quietly rely on to sleep at night, believing nothing catalogued is on a collision course with us. But that math only holds up if the object really is a plain, silent asteroid. If it's secretly outgassing, secretly thrusting itself off course by even a tiny, near-invisible amount, the model is wrong from the very first calculation. Not dramatically wrong, not overnight. It's a slow, compounding error, one that looks fine for years, even decades, until the predicted path and the real path stop matching entirely. That's precisely what happened to 1998 SH2, and this isn't a one-off case study we can file away and forget. Right now, there are close to 38,000 near-Earth objects cataloged using this exact same gravity-only approach. Every single one of them assumed, by default, to be a normal, silent, predictable rock. Every one of them running on the same blind spot that let 1998 SH2 vanish from a precisely targeted radar scan, on schedule, in front of professional astronomers. The researchers behind this study didn't stop at just one object either. They're now proposing something much bigger, going back through the entire near-Earth catalog, applying precision motion analysis to every entry, hunting for any object secretly behaving like a comet instead of an asteroid. Because if one dark comet slipped through undetected for 27 straight years, right under a fully funded, actively monitored program, the uncomfortable question writes itself. Think about what that means for the objects we consider settled. Every rock with a long, quiet observation history gets treated as low priority. It's already mapped, already understood, already filed away as safe. 1998 SH2 had that exact profile. 27 years of a clean record was the very thing that made it invisible to suspicion. The objects we trust the most, it turns out, might be the ones we've checked the least. How many others are doing the exact same thing right now, completely unnoticed, while we assume they're perfectly predictable? There's already a next step being built for this exact problem. NASA's NEO Surveyor, the first space telescope purpose-built for planetary defense, is designed specifically to catch faint, dark, low reflectivity objects like this one, long before they become a problem decades down the line. Objects that don't glow. Objects that don't grow a tail. Objects that don't announce themselves in any way at all. Objects just like the one that quietly, invisibly broke the rules for 27 straight years without a single person noticing. Until then, the work falls back on the kind of painstaking archival digging that cracked this case open. Engineers combing back through decades of old images and old numbers, looking for the one object whose past doesn't quite add up. It's slow, it's unglamorous, and based on what just happened with 1998 SH2, it might be the only thing standing between routine asteroid and a very unpleasant surprise. So think back to that radar dish in the California desert, pointed at empty space where a well-known, thoroughly catalogued asteroid should have been sitting. That moment wasn't really a failure of technology. In a strange way, it was the moment the safety net did its job, catching the gap for once, instead of quietly missing it forever. The unsettling part is how close it came to not being caught at all. One radar pass on one ordinary evening, aimed at one supposedly boring rock. If that scan had happened a little differently or a little later, this discovery might never have surfaced. One 9-year observation gap almost swallowed the evidence for good. So here's the real question nobody's answered yet. Out of the roughly 38,000 objects we're tracking right now, using math that assumes every single one of them is a silent, predictable rock, how many are already drifting quietly off the path we think they're on? We won't know. Not until the next one goes missing from a radar screen too. And by then, the question won't be whether dark comets exist. It'll be how many of them we already trusted, filed away, and stopped watching.